Welcome to Session 6.0, Water Heating. This EMSI training section covers energy basics on water heating. Your presenter is Rick Mitchell. This module will give you an understanding of energy use for water heating in the residential, business, and commercial sectors. Water heating is an incredibly valuable but energy-intensive service employed at all levels of industry. Typical domestic uses of hot water are for cooking, cleaning, bathing, and space heating. In industry, both hot water and water heated to steam have many uses. This presentation will cover the areas regarding water heating technologies and the theory behind the heating. Water heating technologies. Hot water systems for the domestic supply of hot water fall into two main categories: storage water heaters and instantaneous water heaters. Each of these have their own advantages and disadvantages. The decision of which one to choose mainly depends on the customer's requirements. Other types of water heating that we'll look at are solar water heaters and heat pumps, which work in conjunction with water heating units. There are two types of storage water heaters: electric-powered and gas-powered storage water heaters. Both types will be discussed further into the presentation. Also, with instantaneous water heaters, there are two types: electric and gas-powered instantaneous hot water systems. Both types will be discussed. Heat pumps remove energy from a low temperature source and move it into a high temperature hot water tank. And solar water heaters can be grouped into two different groups: closed coupled thermosiphon hot water systems and forced circulation systems, or mains pressure pumped water heaters. Storage water heaters allow heated water to be stored in an insulated tank ready for use when required. Water is heated to temperatures between 60 and 70 degrees Celsius, and hot water is drawn from the top of the tank and replaced by a layer of cold water at the bottom of the tank. The temperature drop is sensed by a thermostat which turns on the heater at the bottom of the tank. Although the tank is insulated, it's constantly losing energy, so the hot water temperature drops over time until it's reheated. If hot water is drawn faster than the cold water can be heated up, the cold layer will eventually move to the top of the tank. Excluding solar, which will be covered later, there are two main types of storage water heaters: electric storage and gas storage. Most electricity providers offer a choice of tariffs for water heaters: a day rate supply and a night rate supply. A 4-person household needs a tank of approximately 125 to 160 litres. The disadvantage of such a system is its high running cost. Gas storage water heaters are available in standard or high-efficiency models. The high-efficiency models may be more expensive to buy, however they are more environmentally friendly and more cost-effective to operate. These gas heaters need only small tanks, as gas is available 24 hours a day and heat losses can be replaced quickly. For a 4-person household, one would only need a tank of approximately 135 to 170 litres. They can be installed externally or internally with a flue. When comparing gas and electric-powered systems, both have a relatively high installation cost. However, electric-powered systems have a higher operating cost. This will only increase in coming years as electricity prices in Australia continue to rise. The higher operating cost is attributed to electric's higher energy consumption needs. Therefore, gas-powered systems are much more efficient than electric systems. Electric-powered systems can also produce up to 30% more greenhouse gas emissions than gas-powered installations. In many parts of Australia, electric hot water heating systems are in the process of being phased out. This table indicates suitability of storage tank capacity for different household sizes, depending on the tariff used. For commercial operations, larger demands can be satisfied by connecting several smaller tanks in order to provide appropriate volumes of water. For example, a hotel catering to 200 customers may require 8,000 litres of electric storage water heating. This could be supplied by 20 400-litre tanks, each in parallel. Instantaneous water heaters, or continuous flow hot water systems, only heat water when it is needed and do not use a storage tank. When a tap is turned on, cold water flows through a heat exchanger, igniting a gas burner or switching on an electric element. There are no losses, and an unlimited supply of hot water is available as long as there is gas or electricity available. Flow rates of hot water can vary from 6 litres a minute to 26 litres a minute, depending on the model. Instantaneous hot water systems can be broken down into two types: electric instantaneous and gas instantaneous. Electric instantaneous water heaters have to be linked to the day rate tariff, resulting in an increase in the running costs compared with an off-peak storage system. On the other hand, since there is no tank to lose heat, they are cheaper to run than day rate storage heaters. In older gas instantaneous water heater models, the water temperature varied depending on the water flow. The more cold water running through the heat exchanger, the lower the temperature. However, modern systems have electronic controls to ensure a constant temperature up to the model's maximum flow rate. The temperature will only drop if water is drawn at a higher rate than max flow rate. Since there are no tank losses, they are more cost-effective to run than gas storage systems. When comparing storage systems to instantaneous systems, storage systems are more suitable for applications where there is a smaller demand for hot water, whereas instantaneous systems are more efficient where a higher demand is present, as the water is heated immediately, therefore never running out of water. There is a greater opportunity for long-term energy savings from an instantaneous system because water is heated on demand. Storage systems take up more space as they require a tank to store the water. Even though instantaneous systems have a startup delay, they can provide an unlimited hot water supply. One drawback of instantaneous heaters is that they depend on the water pressure delivered from mains connection and cannot be increased. Therefore, if the original pressure is low, the hot water will be supplied at the same pressure. One system is not necessarily superior to the other. It is more a matter of matching your client's needs to an appropriate system. A heat pump water heater removes energy from a low temperature source, such as ambient air or wastewater, and moves it to a high temperature hot water tank. Electricity is used to drive the compressor and the fan, but not to actually heat the water. Heat pumps operate in a reverse manner to a refrigerator or an air conditioner, expelling cool air to the environment and transferring heat to the water tank. Air source heat pumps are the most common heat pumps in Australia. Heat pumps can significantly improve the efficiency of electric storage hot water systems. Assuming the efficiency of an electric heating element is 100%, the efficiency of a heat pump water heater would be in the range of 250% to 450%. The heat pump's peak electrical power demand is 500 to 800 watts, whereas the electric water heater's peak power demand is between 2,400 to 4,800 watts. So how does a heat pump work? In general, the heat pump uses the heat from the air, absorbs it, and then transfers the heat to the water in the tank. However, there are a few more steps involved to do this. Firstly, a liquid refrigerant with a low evaporative temperature is passed through the evaporator, where it absorbs the heat from the air and is converted to a gas. Secondly, the gas refrigerant is compressed using an electric compressor. The compression causes the gas temperature to increase so that it becomes hotter than the water in the tank. Thirdly, this hot gas flows into a condenser, where it transfers the heat to the water. And lastly, the gas flows into the expansion valve, where its temperature then drops and returns to liquid form. The cycle starts again as the liquid flows into the evaporator. Some advantages to heat pumps is their easy changeover installation. There is no need for special electrical sockets or roof or orientation space needs. It can supply more heat energy than the electrical energy that it actually consumes and has very low greenhouse gas emissions. Some disadvantages include its high capital and installation costs. Heat pumps are climate sensitive, meaning that its performance is reduced in colder ambient air temperatures, which reduces energy efficiency and produces slower rates of water heating. Their systems can be relatively complex, which may influence their durability and reliability as customers may not know how they work. They also may require a more expensive electricity tariff to operate effectively. Heat pumps can also be noisy. Solar hot water heaters use the sun's energy to heat water by capturing it in a solar collector and cycling this heated water to a tank. They are entitled to a number of small-scale technology certificates, or also known as STCs, under the Small-Scale Renewable Energy Scheme. The number is based on the estimated amount of electricity in megawatt hours the system displaces over the course of its lifetime. Most owners assign their STCs to registered agents and in return receive a financial benefit, often in the form of a discount off the invoice price. STCs are covered in further detail in the legislation module. Solar water heaters are available in two different system configurations: forced circulation systems, also known as mains pressure pumped systems, and closed-coupled thermosiphon systems. The configuration of a forced circulation system uses a pump system with a tank situated below the level of the collectors. Water must therefore be pumped from the tank to the collectors and back by a thermostatically controlled pump. Pumps are not expensive to run, costing between 1 and 2 cents per hour. This system is feasible where the roof is not strong enough to support a closed-coupled system. The closed-coupled thermosiphon solar hot water system is the most common system on the market. It consists of mounted solar collectors combined with a horizontally mounted storage tank immediately located above these collectors. In most solar systems, a pump is not required. Heated water rises naturally through the solar collectors and enters the storage tank. When this happens, cooler water at the base is pushed out and flows down the bottom of the collectors. Cycle is continuously repeated while the sun is shining. Most commercially available hot water systems employ this cycle, commonly referred to as thermosiphon flow. If hot water use is required at night, a one-shot booster provides hot water as needed. We will cover this shortly. Two common types of solar collectors are the flat plate collectors and evacuated tube collectors. Both serve the same basic function of collecting heat. Flat plate collectors are available in glazed and unglazed varieties. Glazed flat plate collectors use solar energy to heat liquid that circulates in an insulated solar loop. These collectors are better suited for moderate temperature applications where the demand temperature is between 30 to 70 degrees Celsius and for applications that require heat during the winter months. They are most commonly used for the heating of domestic and commercial hot water, buildings, and indoor swimming pools. Unglazed flat plate collectors are best suited for low temperature applications where the demand temperature is below 30 degrees Celsius because they are not insulated. By far, the primary market is for heating outdoor swimming pools, but other markets exist including heating seasonal indoor swimming pools, preheating water for car washes, and heating water used in fish farming operations. Here we have a quick comparison of flat plate and evacuated tube collector solar water heaters. Flat panel systems are less efficient and cannot be used in freezing temperatures, whereas evacuated tube systems can. Evacuated tube systems only require a small roof area and have very little corrosion issues, unlike the flat panel, which requires more roof space and suffers from corrosion problems. Although the evacuated tubes are more costly, they are by far the better choice compared to flat plate collectors, in terms of both efficiency and reliability. What if there is little or no sunlight available? In this case, a one-shot booster is used with the solar hot water systems, which most of them come equipped with. The booster is an electric heater switch that can be turned on during periods of low sun. It turns the heater on for a specific time, allowing water to heat and then turns off again. Water heating theory. Heat energy is a form of heat which transfers among particles in a substance or system by means of kinetic energy of those particles. Heat transfer normally takes place from a high temperature object to a lower temperature object. This heat transfer is generally referred to as heat flow. The watt, which is the SI unit of power, can be defined as 1 joule per second of heat flow. A calorie is one of the units used to quantify heat energy. It is defined as the amount of heat required to change the temperature of 1 gram of liquid water by 1 degree Celsius. 1 calorie is equal to 4.184 joules. Specific enthalpy is the term given to the total energy due to both pressure and temperature of a fluid such as water or steam at any given time and condition. More specifically, it is the sum of the internal energy and the work done by an applied pressure. The basic unit of measurement is the joule, J. Since 1 joule represents a very small amount of energy, it is common to use kilojoules or kJ. Specific enthalpy is a measure of the total energy of a unit mass. The unit commonly used is kilojoules per kilogram. Heat capacity of a system is the amount of heat required to change the temperature of a whole system by 1 degree. Specific heat is the amount of heat required to change temperature of 1 kilogram of a substance by 1 degree. Specific heat is measured in kilojoules per kilogram, degrees Celsius. The greater specific heat capacity, the greater amount of heat will be absorbed by that substance. Water has a very large specific heat capacity compared with many fluids, making water a good heat carrier. Since we will only be dealing with water heating calculations, it's best to memorize the magic number 4.18. This is basically a constant and represents the specific heat capacity of water measured in kilojoules per kilogram, degrees Celsius. The energy required to raise the temperature of a system of mass, or m by delta T, is Q equals mc delta T. Remember, in a closed system, heat gained by one thing equals the heat lost by another. This formula states that Q, or heat transfer, is equal to the mass of the liquid multiplied by the specific heat capacity, and again by the change in temperature. To convert kilojoules to kilowatts, in order to make it useful, we must divide by 3,600. So taking the familiar equation kilowatt hours per annum equals P on eta by time, we can substitute the new equation. To reduce the power consumption, we'll first look at altering the mass of the water being heated. This number is mainly influenced by the use patterns of the user. To reduce the amount of water used or heated, some recommendations you can make to your clients include: use only the water that is required to do the job, install efficient water fixtures, install flow rate restrictors in taps, and use cold water or cold washing when possible. The next variable that can be influenced is change in temperature between the initial temperature of the water to be heated and the final demand temperature. The temperature difference is influenced by the technologies and the behavioral habits of consumers. The temperature difference can be reduced by installing a tempering valve, which limits the final demand temperature based on the intended destination. Tempering valves are now a requirement for all new hot water systems as per AS 3498, the Australian Standard Authorization requirements for plumbing products, water heaters and hot water storage tanks. It states that for early childhood centres, primary and secondary schools, nursing homes or similar places, the delivery of hot water for personal hygiene shall be limited to 45 degrees Celsius. For all other buildings, it should be limited to 50 degrees Celsius. The efficiency variable is mainly a function of the type of system and technologies installed. Efficiency can be improved by upgrading to more efficient technologies or changing technologies to match appropriate applications. It can be also improved by reducing the heat losses in the system. To reduce heat losses and therefore improve efficiency, you can insulate hot water piping, position hot water systems in insulated rooms or in areas that receive direct sunlight, therefore increasing the ambient air temperature, or reduce delivery distance from heat source to destination through efficient piping design. The time of water use in a household or a small to medium enterprise also depends on consumer behavioral habits. To reduce the amount of time that water is used, the two main solutions are to close taps when not in use and repair leaking ones. Here are some example scenarios. Example scenario 1. How much heat is required by a commercial storage electric heater with an efficiency of 100% to raise the temperature of 5,000 litres of water from 25 degrees to 80 degrees Celsius? Remember that 1 litre of water is equal to 1 kilogram of water. To solve this, first state what's known. The mass of the water is 5,000 kilograms. The change in temperature, or delta T, from 25 to 80 degrees is 55 degrees. And the heat capacity of water is 4.18 kilojoules per kilogram degrees Celsius. Then input the values into the formula to reach a value of 1149.5 megajoules. We know that 3.6 megajoules is equal to 1 kilowatt hour. So to display this in kilowatt hours, simply divide the value by 3.6. The final answer is 319.3 kilowatt hours. Example scenario 2. Using the same example, consider the implications if the unit has a coefficient of performance of 3. Using the same calculation as the previous question, we know that Q is equal to 1149.5 megajoules. Now to account for the COP. We divide the total energy by the COP, which gives us 383.1 megajoules. And converting back to kilowatt hours gives us 106.41 kilowatt hours. Example scenario 3. 50 litres of water is heated with a 48 kilowatt boiler from 10 degrees Celsius to 100 degrees Celsius. Calculate the time it takes for the water to boil. The energy required to heat the water, Q, is equal to 50 kilograms mass of water multiplied by 4.18 kilojoules per kilogram degrees Celsius, multiplied by a temperature change of 90 degrees Celsius. This equates to 18.8 megajoules. We know that time equals energy divided by power, and we know that the boiler power is 48 kilowatts. So first we have to solve for the energy. The energy will be equal to the boiler's rating multiplied by 3,600, which is equal to 172,800 kilojoules per hour. Dividing by 3,600 will convert the number back to seconds, which in this case is again 48 kilojoules per second. Therefore, using the formula for time is equal to power divided by energy, 18.81 megajoules is divided by 48 kilojoules per second. The total amount of time to heat the water is equal to 392 seconds, or approximately 6.5 minutes. Example scenario 4. The same principle holds true for cooling. For example, a 50-litre tank of soft drink is placed in the refrigerator where it is cooled from 20 degrees Celsius to 2 degrees Celsius. Assuming soft drink has the same specific heat capacity as water, and the refrigerator has a coefficient of performance of 2.5, calculate the energy it takes to cool the soft drink. The total energy equals a 50 kilogram mass of water multiplied by 4.18 kilojoules per kilogram degrees Celsius, and again by a temperature change of 18 degrees Celsius. The total energy will equal to 3.76 megajoules, which, divided by 3.6 megajoules kilowatt hours, is 1.045 kilowatt hours. To account for the efficiency of the refrigerator, divide this number by the COP, which equals to 0.418 kilowatt hours. To continue with presentations, please select Energy Session 7.0, Cleaning, from the navigation bar. To complete the assessment for this presentation, please select Tutorial 6.0, Water Heating.